So I'll be talking about constructions and performance of hyperbolic and semi-hyperbolic Floquet codes. And this was work completed while at UCL with Nico. So the motivation here for this work is to reduce the overhead of quantum error correction. As we know, fault-tolerant applications require many millions of qubits, and surface codes and honeycomb codes incur an enormous overhead. And so the Floquet codes we've heard about from today have a very high overhead, as shown by this plot from a work from a couple of years ago by Higgott et al. And so this is just showing the teraquop qubit count, which is just the number of physical qubits per logical qubit required to implement around 1 trillion logical idling operations as a function of the physical error rate. As we can see in these two different noise models, like the left one here is assuming you can use CNOT gates and measurements, single qubit measurements, and the right-hand plot is assuming you can directly measure 2-qubit Pauli operators. In both of these noise models, we require either thousands or tens of thousands of physical qubits per logical qubit for these Euclidean Floquet codes. And so one potential solution to reduce these qubit overheads is looking at LWC codes, which we've heard about a lot about this week. And here we're just looking at some LWC code is some stabilizer code where the only constraint is that the degree of this Tanner is constant. And this is just a high-level summary of some of the families of codes, or families of codes, which can greatly improve on the torus code, such as, for example, the hypergraph product code from over a decade ago, where we have a linear dimension k in the number of physical qubits and the square root distance, and of course all these very exciting recent results of lifted and balanced products and quantum Tanner codes, where we have a dimension and distance both linear in the number of physical qubits. Now I'll be talking about hyperbolic codes, which at first glance might not look quite as exciting as these recent asymptotic results. I mean, they have a linear dimension k in the number of physical qubits, but only a logarithmic distance. But for practical purposes, we care about the finite system size performance and not the asymptotics. And it turns out that some families of these hyperbolic codes can have very good performance in practice for the sort of finite system sizes we care about and for the logical error rates we care about. So I realize many of you are already very familiar with torus codes and hyperbolic surface codes, but I'll just give a brief summary on this slide. So it's already been known for many years that we can derive codes from more general surfaces than just the torus code. So the torus code is derived from the tiling of a torus, where we associate, and for both these hyperbolic surface codes and torus codes, in this diagram we're associating a qubit with each edge, and then a Z stabilizer with each face, and an X stabilizer with each vertex. And so the genus, the number of logical qubits encoded in a torus code is just in a surface code of some general surface is just twice the genus. And so for a torus code, as we know, we just encode 2 logical qubits associated with a single handle. The motivation for hyperbolic surface codes is that the genus now scales with the area of the surface, and as does the number of physical qubits. So we end up with a finite encoding rate k over n, but with a reduced distance, which is logarithmic in n. This does turn out to be a slight asymptotic improvement over torus codes, despite the reduced distance. But yes. But in practice, we need a circuit, not just a code. And so if you try to schedule a hyperbolic surface code, you can end up with obviously a deeper syndrome extraction circuit than a regular torus code. And as Michael Bevelin was mentioning earlier this week, you can have the problem of hook errors. So some single qubit Z error in the syndrome extraction circuit might propagate through, say, to 2 Z errors on the data qubit at the end of the circuit. These deeper syndrome extraction circuits can also reduce the noise threshold of the code and introducing more potential error locations. And so we care about a circuit, not just a code. And so this quantum circuit is constrained by the idling, gate, and measurement noise of the device, and the native physical operations and the qubit connectivity, both the degree of connectivity and the geometric locality. And so in this work, we're looking at in some sense, we're looking at improved circuits for hyperbolic codes for some certain noise models. And so in previous work with Nico from around 3 years ago, we looked at subsystem versions of hyperbolic codes, where we reduced, as I mentioned before, the high check weight of these hyperbolic codes can lead to problems when scheduling them and generating syndrome extraction circuits. So in previous work, we looked at these subsystem hyperbolic codes where we reduced the check weight to 3, by measuring these gauge operators rather than the stabilizers directly of the hyperbolic surface codes. And we showed that this led to a kind of an over 4 times saving in qubit overhead for circuit noise with sort of pseudo thresholds above 0.5%. And this flexibility arises from allowing you can think of it as this flexibility arises from allowing the instantaneous stabilizer group of the code to vary over time. So you're essentially switching between 2 hyperbolic surface codes, like of the primal and a dual lattice in each cycle. However, the logical operators do remain fixed. And so in this work, we're just looking at can we do even better using the recent results on Floquet codes, and how much better can we do in these different noise models that are more amenable to the Floquet codes that we've heard about today. So that's what this talk is about. So we take the toric honeycomb codes, and then we look at deriving these from more general surfaces of these closed hyperbolic surfaces. And the summary is that we find that these codes can be between 5 and 50 times more efficient than these toric honeycomb codes, depending on the exact details of the noise model, and up to 100 times more efficient than surface codes if you look at like a pair measurement noise model. And all, these are just Floquet codes, so all the properties of Floquet codes hold with all the nice properties of weight 2 checks and degree 3 connectivity. It also implies a biplanar or modular architecture, and also efficient decoders. So we think these are very practical codes. And they also have a very high threshold in a particular noise model where you can make these direct 2-qubit Pauli measurements. So I'll give another an overview of Floquet codes, which, but maybe from a slightly different perspective, as you heard this morning, looking at more from the perspective of subsystem codes. So Floquet codes are defined on a 3-colorable lattice, where each edge is the color of the faces it connects, as shown on the right here. And so we measure these weight 2 anti-commuting checks, shown on the right. So XX on the red edges, and YY on the green, and ZZ on the blue. Now, if you were to use these to define a subsystem code, and a subsystem code is defined by some set of so-called gauge operators, which are just Pauli operators, which don't generally commute, then the stabilizers of the subsystem code that define the code space are just products of the gauge operators which commute with all the gauge operators. And so if you look at what these stabilizers are of this subsystem code, you see that they are just all the cycles of the edge operators. But then if you look at what are these cycles, and then if you use these to define some stabilizer code, and then you look at what is the code space, you realize that these homologically non-trivial cycles are also stabilizers of this subsystem code. And therefore, you end up with no logical degrees of freedom. And so the result of Hastings and Ha was to show that when you choose this Floquet code schedule, where you measure XX on the red edges and YY on the green and ZZ on the blue, it turns out you don't measure these logical degrees of freedom. And this figure from Christoph's paper is one explanation of why this is the case, because you can show that through the schedule, you only ever measure these bicolored cycles of over here, for example, red-green and red-green edges. And so these bicolored cycles are by definition homologically trivial. And so therefore, the homologically non-trivial cycles are preserved, they're not measured. Now, as was mentioned today, there's a close mapping between these Floquet codes and toric codes, or I'll refer to them more generally as these embedded homological codes here, since we're looking at, since they're mapped to hyperbolic surface codes in our more general Floquet codes. So here I'm just going to explicitly showing the mapping, how you can map a honeycomb code to a toric code. So here you can see each edge. So let's suppose you've just measured the red edges in your Floquet code schedule. That projects this red edge into a 1-qubit subspace after measurement. And you can think of this as forming an effective qubit in some embedded homological code. So for example, here, this red edge, once measured, has an effective Z operator given by a physical IX Pauli operator. And this effective qubit is a qubit in this kind of restricted lattice, this dotted black lattice here, this hexagonal lattice. And so the homological code associated with this, this is surface code, the hexagonal surface code associated with this dotted lattice, the qubits of this embedded code are these effective qubits shown here, associated with the edge just measured. And this is one way you can derive the logical operators of the honeycomb code, shown as in the left 4 figures here, in the left box here. And so I'm just showing the 4 logical operators of the honeycomb code. And so each one is associated with some homologically non-trivial cycle through the tiling. Now these logicals do evolve over the schedule, but you also have these inner logical operators, which are formed from products of the basis for logicals shown on the left here. And these logicals are fixed over the course of the schedule. But there is no basis for the logical operators. There is no complete basis for the logical operators, which remains fixed throughout the cycle. And then, as Ben mentioned earlier, we can decode Floquet codes by defining these detector cells, where we compare a stabilizer. We compare 2 consecutive measurements of stabilizers. So here you can see that the detectors are formed from the parity of 12 edge measurements spanning 5 subrounds, where each subround is just one measurement of the edge operators. And so you can show that any physical error in the circuit will violate of X type or Z. Well, yeah, you can decompose this error model into what's called like a graph-like error model and decode it with matching, where the sort of the important error mechanisms violate at most 2 detector cells. So yeah, in this work, we're looking at constructing these Floquet codes from hyperbolic tilings, which was kind of proposed by Christophe in this paper from this planar Floquet codes paper from 2021, where he pointed out that the asymptotic parameter scaling of these codes should be the same as hyperbolic surface codes because of this mapping to the embedded homological code. And so I mentioned before that we do have some asymptotic advantage relative to toric codes, and that can be understood from the fact that this ratio kd squared over n is log squared n for the hyperbolic codes, but just constant for honeycomb codes. So we do have some small asymptotic advantage relative to honeycomb codes. And in this work, we're showing that actually the constant factors are also very good. And so yeah, prior to our work, sort of explicit examples of these codes have not been studied, nor their performance in more realistic noise models. Okay, so what tilings do we consider? Well, we use Wittoff's kaleidoscopic construction to construct several, sort of 3 families of hyperbolic tilings. So these tilings are generated through reflections across the side of a triangle, as shown on the right here. So we have this triangle with internal angles pi over 2, pi over 4, pi over 5. And reflecting in the sides of this triangle, we can generate with this kind of vertex in the center, we can generate this 4, 8, 10 uniform tiling shown on the right here, top right here. So I say 4, 8, 10 because around each vertex we have faces of sides 4, 8, and 10. And so more generally, we can generate an R.G.B uniform tiling from a triangle group generated in this way. And then we can construct finite tilings from taking quotients of this group. Essentially, we identify triangles related by some translation in the tiling. And this tiling is hyperbolic if 1 over R plus 1 over G plus 1 over B is less than a half. And so these are the 3 different tilings we consider, the 888, the 4810, and the 41010 tilings. I just need to now define the distance we consider in some of the numerics that we show. One of them is we define as the so-called embedded distance. And that's just the minimum distance of any of these 3 embedded homological codes. So after any of the 3 different subrounds, we have some slightly different embedded homological code with a derived, defined by this a tiling shown by the dotted black lines. And so we find the distance of these 3 different codes for each tiling and use that to define the embedded distance of the Floquet code, which roughly corresponds, or almost always corresponds, to the circuit distance in this pair measurement noise model. So the smallest example we found that is quite promising for very sort of near-term experiments is this Bolza Floquet code, which is derived from the 888 tiling of the genus 2 Bolza surface. And so to understand this, we can, looking at from this figure, we just identify opposite sides of this figure. And And this encodes 4 logical qubits into 16 physical qubits.
Those red faces 6 body?
8, yeah.
Okay.
Each phase, yeah, this is technical.
Okay.
So this.
Oh yeah, there are 8
and I mean, this is just an example for the small code, the examples of the logical operators. So each logical operator is associated with a homologically non-trivial path through the lattice. I'll explain how you how the logical operators are updated in a minute. But essentially, we need both the logical path and the Pauli operators in its support. And so the path sort of remains fixed throughout the schedule, but the actual physical Pauli operator does change. The logical operator does change throughout the cycle, but it remains in the support of this homologically non-trivial logical path. So yeah, this is a basis for the logical operators of the Bolza code. And yes, so the way that the way that you can understand how these logicals change is that after the C sub-round, where C is either the red, green, or blue checks, you multiply the C checks into the logical operator if they lie within the homologically non-trivial logical path. Construct a schedule for some arbitrary surface. Okay. So far, I've explained how we can derive these hyperbolic Floquet codes, but it does have this problem of having a logarithmic distance, and we might need, say, 10 to the minus 12 logical error rates in practice for some quantum algorithm. And so one question is, how can we achieve these low logical error rates with a logarithmic distance? And so we can weaken the curvature using semi-hyperbolic lattices to obtain code families with distance scaling as square root of n. Now we no longer have a sort of, if we define a family of codes this way, we take some hyperbolic tiling and then fine grain it. We no longer have an asymptotic improvement over honeycomb codes. But what we can do is we can achieve some ratio n over k equals cd squared, where this constant c is much better, much smaller than for the honeycomb code. And that's what we do find. So how does this work? We actually fine grain the dual lattice of this 3-colorable tiling. So starting from this 3-colorable tiling, we take the dual, which is this white lines here, or now black lines. And then in each triangle of this dual lattice, we fine grain it with a triangular lattice, and then take the dual again, which is these blue dotted lines. And so then we end up with a 3-colorable tiling, which is fine grained. So we've essentially inserted hexagons into this tiling, which was previously the subtiling. But we do it via fine graining this dual tiling. Now we might worry that by fine graining, we're kind of losing our advantage relative to the honeycomb codes. And it turns out that's not the case. So that's what this plot here is showing. So yeah, the question is, does fine graining reduce the advantage relative to honeycomb codes? So we're boosting the distance in a way that allows us to gain exponential suppression of logical errors, but have we lost the advantage? And so each line here is a family of semi-hyperbolic Floquet codes. And so for example, I'm going to take this green line here. Each dot, so going one point from left to right, is fine graining the lattice by 1, so adding in 1 extra vertex along each edge of the triangle in the dual tiling. So essentially increasing the fine graining by 1. And the y-axis here is essentially the relative improvement over in the parameters over honeycomb codes. So 6k d squared over n is equal to 1 for the honeycomb code. And so, for example, when this is equal to 10, in some sense, you've got a sort of a 10 times improvement in the qubit overhead compared to the honeycomb code. So what we can see is as we increase the distance of these codes by fine graining, this improvement can drop, but sometimes not at all, and when it does, not by much. So, essentially, we still retain a large advantage over honeycomb codes whilst increasing the distance to obtain low logical error rates. We've lost an asymptotic advantage, but we retain a big constant factor improvement. And so now this is another plot showing the parameters of these codes. This is showing the number of logical qubits that you can protect with an embedded distance of at least 6. So for a given number of physical qubits, how many honeycomb codes or semi-hyperbolic codes, how many logical qubits can you encode with either honeycomb codes or semi-hyperbolic codes? And we can see that even with, say, 300 physical qubits, you can obtain a 6 times improvement, and then with 600, 10 to 15 times improvement, and then with 1,400 qubits, 27 times safer. So it's significant improvements relative to honeycomb codes. And I'm about to show you some simulations with this code, which I've circled in red here. So the noise models we consider are these EM3, this EM3 noise model, where we directly measure the XX, YY, or ZZ measurements, followed by 2-qubit depolarising noise correlated with the measurement error. So that was used in these 2 previous works. And it's a sort of Majorana-inspired noise model. And we also consider this SD6 noise model, which is a sort of a standard circuit level depolarising noise model, where we use an oscillar and CNOTs for each edge measurement. So this noise model is more standard, but also much less advantageous for Floquet codes. And so for the small example, what this is essentially showing is that the Bolza code encoding 4 logical operators, 4 logical qubits, has identical performance to 4 planar honeycomb codes with the same distance and the same, the logical error rates essentially match. I think the nicest example is probably this medium-sized example here, encoding 32 logical qubits. So this is from a 41010 tiling using 600 qubits. And we find that, whereas our hyperbolic code requires only 600 physical qubits, an equivalent honeycomb code would require 6,912. And this is also for an EM3 noise model. So for this noise model, using a surface code would be even more expensive. Or another way of putting it is using some other compilation of the surface code to pair measurements other than the Floquet code would be even more expensive. So we save something like a factor of 12 compared to the kind of the best known code for this noise model, using only sort of 600 qubits. And then just a large example, I won't show you the plot, but essentially, if the larger system sizes we constructed, we can obtain around a 50 times improvement over honeycomb codes using around 20,000 physical qubits. And yeah, to obtain like a teraquop regime where you can implement, say, 1 trillion logical idling gates, you only need around 32 physical qubits per logical qubit. Yeah, the codes are they're much less promising if you use a kind of standard circuit level depolarizing noise model. So even using, say, 50,000 physical qubits, you only attain a kind of a factor of 5 improvement over surface codes to get to distance 21. You can beat the surface code with these hyperbolic Floquet codes using the standard circuit level depolarizing noise model, but it's less than an order of magnitude, whereas with this EM3 noise model, it's kind of 1 or 2 orders of magnitude improvement. And yeah, the threshold is, if you consider these families of codes as defined from sort of fine-graining the tiling and looking at these semi-hyperbolic lattices, and they're essentially, locally, they're essentially the same as the honeycomb code, and that's all this plot is showing, is that the noise threshold here for this EM3 noise model is essentially identical to the honeycomb code when you fine-grain the tiling. Okay, so how do you implement this hyperbolic connectivity? Yeah, so all these gates are, of course, local on the hyperbolic surface. And so we propose 2 different ways that you could implement this in practice. One is either using a biplanar architecture or a modular architecture. And so we heard more about this earlier in the week in Ted's talk. But yeah, we consider this situation where we want to use a small number of layers. So we have some qubits laid out in a grid. We want to use a few layers of couplers where the couplers in each layer don't cross, they're planar. But they may be long range. And so it's known from these previous results by Tremblay, Duffos, and Beverland, sort of applying some results from graph theory. It's known that the number of layers, the number of layers is given by the thickness of the qubit connectivity graph, and that's just related to the degree of the connectivity graph, which is constant for LDPC codes. So it's known that you can use some cool small constant number of layers. To be more precise here, so the thickness of a graph is the minimum number of planar subgraphs into which the graph can be decomposed. And then the two results from this paper, which are kind of used here, is one is that the graph of a graph of degree d has thickness at most the ceiling of d over 2. And then any planar graph always has a planar representation in which the nodes are placed in arbitrary positions. And so just directly applying it to Floquet codes, we see that since they had degree 3, that immediately implies that they can be fit into a biplanar architecture. So you can just use 2 layers of couplers between qubits. And that also applies to the subsystem hyperbolic codes as well. And then, so that's then for the modular architecture, we sort of point out that, say, for the semi-hyperbolic tiling, locally, these modules have sort of Euclidean connectivity. And so you could imagine using some small modules with sort of local Euclidean connectivity, like so, essentially sort of small honeycomb codes, but where the boundaries are different. And instead, we use these long-range links between modules to kind of implement the hyperbolic connectivity. And so you could look at, say, how well this architecture might tolerate, say, the noisy links between modules, as has been done in previous work for surface codes. Okay, so compared to other recent work on LDPC codes, such as the practical implementations of hypergraphed and generalized bicycle codes, so these other constructions perform better for standard depolarising noise. So they have a larger saving for smaller system sizes. But the hyperbolic Floquet codes do perform better for the pair measurement noise model. And so, and also it's worth noting that this reference 3 here also constructs hyperbolic Floquet codes using a different noise model, and does contain some new examples. And then to compare with kind of what Ted was presenting on Monday, we have a kind of a similar sort of overhead reduction relative to the surface code or honeycomb codes for slightly larger system sizes of, say, 600 qubits rather than 288. But our advantages come in this different noise model. So there's sort of complementary results in the sense that our improvements arise from this pair measurement architecture, whereas the bivariate bicycle codes have an advantage of the standard circuit level noise model. 2 advantages of our approach. One is that the connectivity degree of the qubit connectivity degree is 3 rather than 6, and it's amenable to optimize efficient decoders such as matching or union find. So for future work, one sort of important area to research will be to look into logical gates in these codes. So you could certainly use adapt techniques which are known for hyperbolic codes, such as Dane twists and lattice surgery, which were shown in reference 1. But there are 2 limitations of these approaches, even for the standard hyperbolic codes, which is that, firstly, the cumulative degree of connectivity increases with the scales with the distance, or either that or you have to increase the number of physical qubits. And as a result, it wouldn't necessarily preserve the biplanarity. So there are improvements to be, these can be adapted to Floquet codes, and there are details to be worked out there, but there are also these caveats. And it would also be interesting to look at sort of constructions which both have good performance for these noise models and also are amenable to full transversal gates. So in conclusion, we constructed these Floquet codes from hyperbolic and semi-hyperbolic tilings. And for pair measurement architectures, we find they're around 50 times more efficient than honeycomb codes and surface codes. And we can kind of reach this teraquop regime with 32 physical qubits per logical qubit. And we've shown there are these small examples with as few as 16 physical qubits, which kind of seem very experimentally feasible. And yeah, all of our constructions are implementable in these biplanar or modular architectures. Yeah, and they're all efficient to decode with sort of matching or union find. So with that, yeah, take any questions.
question? Comments? So back a few slides ago, you defined this notion of like an embedded distance as the distance of like any one of the ISGs, I guess. But we've also seen examples of Floquet codes where that's not a useful guide for like actually like what the actual distance of the Floquet code when considered as a whole would be. So could you comment on that? Like why, like maybe in this case, like that's not an issue?
Yeah, I mean, we did consider the circuit. We computed the full circuit distance as well, just for the smaller codes. But once the circuits get quite large and then also span time, it's quite a computationally expensive set. So I mean, for small system sizes, I mean, I say small, I mean up to hundreds or maybe single-digit thousands physical qubits. The embedded distance always matched the distance for this pair measurement noise model, except for one case where it's restricted by one. And then the circuit level noise model was the sort of the C0 case and single qubit measurements. That's normally between up to a factor of 2 higher. But yeah, we did consider various different distance definitions. Yeah, I guess at the end of the day, it's the logical error rates that matter, and so that's why we sort of simulate.
Does the slope of the graph match what you expect for the distance?
Yes, not most of the time. Yes, in some cases actually it does better than you'd expect. I don't think I have the plot here, but yeah, I think for the largest code we looked at, for example, I think it was distance 12, but the slope coincided with the distance 16 honeycomb code.
I have a question about decoder. For a long time, for this kind of, at least hyperbolic toric code, for the decoder for the hyperbolic toric code was Hastings one, but this was so this was not sufficient for like the performance was not sufficient. That's the reason why people started to use hyperbolic product code.
Are you referring to the 4D hyperbolic?
Yes. Okay.
Yeah, so these are just 2D, so you can see matching.
So for 2D.
Yeah, for 2D is you can always just use matching.
Okay. Thank you.
With this like smallest examples you mentioned, people actually try to make little bits of hyperbolic lattice on superconducting chips, right, by stretching out the resonators and squishing them. Can you like get the smallest example into something existing?
Yeah, we didn't look into. I guess you'd have to have crossing links just because it's a closed surface. Rather, you haven't considered boundaries. Yeah, adding boundaries, you lose the asymptotic scaling and improvement. But yeah, maybe there would be some small examples where you can have a good constant.
So you need like
yeah,
to deal with the boundaries.
Yeah. Yeah, we didn't. It'll be interesting to see if there are some, say, small planar examples which have better performance than encodes.
I'm wondering if we can comment more on logical operation. And so is it possible to imagine that there is a trade-off between the number of logical qubits you put in your code for surface code or for the logical code and the speed of logical operations? Vaguely, if you pack too many logical qubits, it's going to be harder to reach them. So is it possible it's a price to pay? Yeah.
Oh yeah, certainly. So I think I say for LBC codes in general, it seems most promising you'd use them for long-term storage and this is a quantum algorithm where many of the qubits are idle the majority of the time. So yeah, you have to. You don't have fast access to the logical qubits, and the methods like the Dane twist for moving the logical qubits in memory. There's a price to pay. Would also either be connected. I suppose you could improve the speed of access with high connectivity and high cumulative degree.
Okay, so if I want to do memory and computation on the same code, with hyperbolic code, you think you will lose the advantage over 2D surface code? Or?
I guess we don't know how to. Yeah, from what we currently know, you'd have to teleport qubits into and out of the code, say from surface codes or teracodes, which is slow. But that may not be a problem if you're, as I say, if your qubits are idling.
I wonder what kind kind of threshold values did you get, and did these depend on the exact lattice that you used?
The threshold values. Yes, we only looked at a couple of thresholds. I mean, the threshold essentially, when you scale, when you fine grain the lattice, you'd essentially expect it to be identical to that of the honeycomb code. When you you could also look at the threshold in terms of the family of purely hyperbolic tilings, but you don't kind of get a very clean crossing. I mean, the distances are fairly small, and you don't. Yeah, it's kind of hard to give a precise threshold estimate. But if you just fine grain the lattice and define the family that way, then they essentially match that of the honeycomb code. So we did verify that for a couple of examples, but beyond that we didn't.
Thank you.
So did you try to do transversal T gates work on the CCD44? Did they make CCC-CZ? Or,
No, I wouldn't.
On the 3D one.
Yeah, 3D, not on the 2D.
no, but it's. I mean, you have all weight 8 checks, right?
Yes.
You have more embedded.
Yeah, not sure. Maybe we can chat about this after.
One more sort of superficial question. Do I understand correctly that the measurement schedule is the same for any lattices because it's determined by the colors, not by the lattice structure?
Yes.
Yeah. So you
With
did-
one small caveat, but yes, depending on the whether the surface is orientable or not, slightly changes things with the circular noise model. But for the pair measurement noise model, it's identical.
Thank you.
Following Nico's question about the problem of like resolving kind of logical operators when they're too densely packed and there's like maybe log of them kind of hitting the same qubit. If you fine grain by like a log amount, can you like resolve all of that to sort of constant intelligence?
Yes, I think that would help. Not something I've looked into in much detail, but maybe Nico.
I don't know. So there's these kind of corner theorems for hyperbolic surfaces, but I don't quite remember the scale. But yeah, very, very possible.
One last question? No? Let's thank you, Pascal.